We are here to help.
In part 1, we discussed a method for recognizing and solving exact differential equations. Now let's explore a different way to solve exact differential equations. Let's consider the same example we did in part 1, but this time the equation is expanded. In part 1, we showed that this differential equation is exact, so we will not be verifying exactness again in this video. This solution method involves looking for a particular function f of xy, whose derivative is contained in the original equation. Recall from part 1 the functions m of xy and n of xy that we were able to recognize from our equation in standard form. The function f we are looking for will be the common term between the following integrals of m and n. To find this function easily, we can ignore some terms in our original differential equation. These terms are those involving x only, any terms which have a factor of y prime and don't involve x, and any scalar terms. In our equation, this means we can ignore the term negative 9x squared since it involves only x. We can ignore the term y prime since it does not involve x. We can also ignore the term 2y times y prime since it has a factor of y prime and does not involve x. The terms we are left with are therefore 2xy plus x squared y prime. By inspection, this is exactly the derivative of the function x squared y. And as we saw before, this is indeed the common term between the integrals of m and n, and will be equal to f prime of xy. To solve for f, we simply integrate the coefficient of y prime with respect to y. In this integral, we do not need to add the constant c after integrating. Therefore, f is x squared y. All we have left to do is rewrite our differential equation with f and integrate. And we have our final answer.